All right, so we know that Newton's second law says that the sum of the forces is going to be equal to mass times acceleration. What we're going to do is we're going to apply this to a rotating object. That object is rotating counterclockwise due to the torque supplied by this force at this radius distance from the center of its rotation. So we know that the torque supplied by that force is going to be equal to the force times the lever arm, and that lever arm winds up being our radius here because, well, that would be our perpendicular distance from that axis of rotation at the center here. So our torque is equal to Fr, so that means if we solve this for force, that would be equal to the torque divided by the radius. All I did was divide both sides by r. Also know that this thing has some sort of acceleration, and due to that torque that's on it, and we know the relationship between translational acceleration and angular acceleration is a is equal to r alpha. So what we're going to do is we're going to take and we're going to substitute in to F equals ma into our Newton's second law here for translational, and what we get is that sum of the torques over the radius, all I did was take this equation here and plug in torque over radius for force, is going to be equal to mass times r alpha. All I did was take r alpha and substitute it in for acceleration, multiply both sides by r, and what we get is the sum of the torques is equal to m r squared alpha. All I did was multiply both sides by r, so I get r times r over here, and I get m r squared alpha. Well, this quantity here, mr squared, that is something called the moment of inertia. Moment of inertia. It is abbreviated r, and again, we're going to calculate that as I, which is going to be equal to mr squared. What that moment of inertia is it is an object's resistance to a change in its rotational motion. So that is a resistance to an object's, do this. All right, it is an object's resistance to change its rotational motion. So really this right here is Newton's whoops, let's do this. That's not quite the final form I want. So if I is equal to mr squared, or moment of inertia is mr squared, then what we get is that sum of the torques is equal to I alpha, and that is the second law for rotational motion. Let's talk a little bit more about that moment of inertia. The moment of inertia is dependent upon the shape, more or less. So I is shape dependent. And dependent on where the axis of rotation is. So some different moments of inertia for different shapes have already been determined. So let me go ahead and give you the equations for those. We've got a hoop, basically a hoop, with the axis of rotation through the center. And the moment of inertia for that is equal to I mr squared. If we take a solid disk, again with the axis through the center, so that's a disk. Moment of inertia is going to be equal to 1/2 mr squared. For a solid sphere, axis of rotation through the center of it. This is a solid sphere. That moment of inertia is 2/5 mr squared. You'll notice that there's always mr squared in the moment of inertia. You might be multiplying it by some fraction, but it will always have ir squared, or excuse me, mr squared. You can have a hollow sphere with the moment of inertia, or excuse me, with the axis through the center of it. And that moment of inertia is for a hollow sphere. That moment of inertia is 2/3 mr squared. And then for these, I can have a thin rod or a rectangular sheet. So thin rod or a sheet, again with the axis of rotation through the center of it. Those both have a moment of inertia equal to 1/12 the length squared. So it's got, again, it's not a radius necessarily, but a distance squared. And that L, that length, is the length of the rod or the length of the sheet. And then you can also have, for a thin rod with the axis rotation, thin rod or a rectangular sheet with the axis of rotation at the end, at one end. Again, L is the length of the rod, but the moment of inertia is going to be equal to 1/3 ml squared. Again, L is the length of the rod or sheet. L is that length. All right, so at some point maybe I'll get to a couple of examples, but these are the notes that I would have given you today had we been in school.